Log on, tune in, find out. Another good idea from Cambridge.
Jordan's theorem on finite linear groups.
Okay, thank you. All right, so this talk will be mostly a historical talk. So I did some historical research. I looked into a very old paper of Jordan from 1878, and I managed to read his original proof of that theorem. So it's a very well-known by now, very well-known theorem, which is usually taught with a different proof. So I will tell you both proofs today. So first I'm going to tell you what that theorem is about. So Jordan's theorem. From 1878. So you start with the G. G is a finite subgroup. Of G, L, N, K. Okay. Let's say G, L, and C. Okay. And yeah, G is a finite subgroup of G, L, and C. Then the conclusion is that G has a normal abelian subgroup A, whose index inside G is bounded by a function which depends only on n. So there exists a function f of n such that if you take any subgroup, any finite subgroup, okay, of G, L, and C, then G has a normal subgroup of index bounded by f of n. So that's here I put G, L, and C because it's actually not true if you change the field. So if you take, for example, of course, a finite field, so if you take Z mod PZ, then this is not true, right? If you take SL2 Z mod PZ, if P is very large, then you will not have such a bound, right? SL2 Z mod PZ has very few subgroups, in fact. It's almost simple. Okay, so you cannot find a large abelian subgroup inside. So this theorem was proven in 1878, and I think Jordan was originally motivated by a problem about differential equations. And the group, so he was looking at differential equations so linear differential equations where the coefficients are given by rational functions. And he was assuming that the solutions were algebraic functions. And in such a situation, then you have a monodromy group. Okay, and this monodromy group belongs to G, L, and C, where n is the degree of the linear equation. And therefore, if you have some so the fact that the solutions are algebraic tells you that the group is finite. The monodromy group is finite. And so if you have such a piece of information on finite subgroups of G, L, and C, then you can deduce some nice information on the solutions of such differential equations. And this is what Jordan was initially interested in. Okay. So today, nowadays, the classical, the way this theorem is proved in textbooks, the proofs you can find in textbooks do not follow Jordan's original argument. They follow a later argument due to Bieberbach and Frobenius. From say 1905, and this is essentially a geometric argument. I will come back to it. I will explain. While Jordan's theorem was essentially Jordan's argument was completely algebraic. So I will start by explaining Jordan's original argument, and then I'll come back to the geometric argument. And perhaps before I do that, I'll explain why I was interested in that theorem. It's been an ongoing project with Ben Green, with Terry Tao, and Tom Sanders for several months, a few years already. That we are trying to approximate group theory. So we're trying to understand the structure of approximate groups. So approximate groups are finite subsets that are not stable under multiplication, like a group, but almost. So we gradually realized that whenever you have a statement in group theory, then and a proof in group theory, then it's likely that this proof will be that you will manage to approximate it somehow to get a statement about approximate groups. Okay, so here is a dictionary, there is somewhat a dictionary between groups and approximate groups, and so here is the analogous statements that we can prove. So this is a joint work with Ben Green. So let A be a finite subset of U n of C. So these are the unitary matrices. Okay. Then okay. Yeah. So assume that A times A times A is less than K times A. So this is the number of elements in the threefold product, and this is a parameter K. So this is what I will mean by approximate group. This is like a finite set which is almost closed under multiplication in that sense. Then the conclusion is that essentially it's the same kind of conclusion as Jordan's theorem. So you will be able to find an abelian subgroup which contains most of A. So in the following sense, in fact, there is S, an abelian subgroup. In fact, it's going to be a root torus. So it's going to be a diagonalizable subgroup of UN of C, given by, so it's not necessarily the full diagonal subgroup, but it's given by the equality between different eigenvalues, such that A is contained in the normalizer of S, and the projection, so if you look at the projection from n of S modulo this, then pi of A is less than, so we have an explicit bound here, e to the c n to the 4, k to the power c n to the squared. C is an absolute constant that we can determine explicitly. So this means that you see, so the normalizer of a torus is only slightly bigger than a torus, but you see that if you mod out by the torus, then you get into a really tiny set. So this really means that A is contained in one coset, so that one coset of S contains most of A. Okay. So this is essentially the structure of approximate subgroups of UN of C. Okay, so it's the approximate analog of Jordan's theorem. Okay, and Yeah, and it turns out that the proof of that theorem follows very closely the Bieber-Barr-Frobenius proof, Jordan's theorem. Okay. Okay, so now we have also with joint work with Terry Tao, we have a more general version of that theorem in GLNC. So somehow that theorem can be generalized if you, instead of looking at unitary matrices, you look at general matrices, GLNC. Then essentially the same kind of theorem holds, but the conclusion is slightly different. You may be stuck into a nilpotent subgroup instead of being stuck in a abelian subgroup. Okay. Okay, in that work so here we get really explicit constants, and whereas in the general GLNC situation we don't have such an explicit dependence on the parameters. Okay, so let me go back to Jordan and let me try to explain how one can prove such a theorem. Okay, so it's a very classical theorem. After Jordan, a lot of people started to look at it, starting with Bieber, Barr, and Frobenius. Then you had Blichfeld, and then the proofs were, and then people sort of forgot about it for a while, and then Larsen and Pink about 15 years ago found a new proof, and after the classification of finite simple groups became available, people started to take a new look at this problem using the classification of finite simple groups. In particular, Weisweiler looked at this problem, and he left a manuscript in 1985, and then suddenly disappeared. So he disappeared while hiking in the Indies. But this manuscript was found by various. I mean, some people had access to this manuscript, and then using the classification of finite simple groups, you can give very good bounds on f of n, and this is what Weisweiler did. Okay, and this was taken up later on by a mathematician from Oxford, Michael Collins, who got the best possible bound. So you see here that an obvious subgroup of GLNC is the permutation matrices, right? In fact, the permutation matrices Sn acts on C to the n minus 1, right? It acts, the standard permutation, when you permute the coordinates, you will stabilize the hyperplane given by the sum of the coordinates equals to 1. So you have this permutation action on a subspace of dimension n minus 1, and this is basically and we know that Sn does not have subgroups of abelian subgroups of large index. So this is the worst case. Okay, and this is what Collins established. So he proved that f of n can be taken to be n plus 1 factorial as soon as if f is large enough. So I think he has this bound, and if n is less, then he has a complete description of what kind of groups can arise. So using the classification, yeah, you have, of course, much better information. Okay, so yeah, so I come to Jordan's original work. So Jordan's idea was Jordan's proof is very close to the proof that the classification of finite subgroups of SO3. So if you look at the sphere S2, okay, and look at the isometries of the sphere, then you can ask what are the finite subgroups of isometries of the sphere. Okay, so this is very well known, and if you read Klein's book on the icosahedron, then he spends he discussed this at length, and he explains this classification into the finite subgroups of isometries of the sphere give rise to Plato's solids, and basically so the finite subgroups of SO3 are you have the dihedral group, you have this cyclic group, and you have A4, you have S4, and A5. Okay, so and these corresponds to the various Plato solids. So A5 is the icosahedron. Then you have the cube and the tetrahedron, okay, and they are dual. So how do you come up with this list? Okay. So one way is to do like this. You suppose you have a finite subgroup of isometries of the sphere. So it acts on the sphere. So you look at every isometry is so let's look at direct isometry. So I'm only looking at rotations. Okay. So every rotation has axis. Okay. So it has two poles, and there are finitely many isometries. So there are finitely many axes. So I can group together the isometries that have the same axis. Okay, so I look at the various axes and I write a class equation. So I write that G is equal to, okay, you have the identity element, and then you have, for every axis that rise as the axis of some non-trivial element of G, you look at the elements that have this axis. So that's exactly the stabilizer of the axis. So the Gx, and of course Gx is the stabilizer of the axis. X, and of course you don't want to count again the identity. So you have such an equality. But then you want to group together the axes that are conjugate to each other. So you're going to write say classes of axes. Okay, and so when you act on an axis, you will. So the group G acts on the axis, and the stabilizer of so this is not the stabilizer of the axis, but these are the when you stabilize an axis, you have two possibilities. You can either swap the two poles, or you can preserve the two poles. Okay. So that these are the elements with X as axis. And then the stabilizer of an axis. Okay, so you see, if you have an axis, then you may have another a rotation that's of angle pi, which flips the two. Okay, but then it will have a different axis than this one. Okay, so in fact, this is either 1 or 2. Okay, whether you flip or you don't flip. So here you write this like this. So you have G over the stabilizer, that axis, times Gx minus 1. Okay, so that's the size of an orbit, and for each element in the orbit, you have the same number of group elements with that axis. So you have this, and this is either okay, and then you rewrite it like this. 1 over this index, which is either 1 or 2. Yeah, so minus 1 over the stabilizer. Okay. Okay. So you get this this nice class equation. Perhaps I go back there. And so this gives you you see it's a Diophantine equation, so it's an equation between every number here appearing there is an integer. So if you divide everything by g, you get some equation of this form: sum of 1 over ni minus b over a, where the ni's are all integers. Okay. So this is what you get, and in fact you have very few solutions, very few possibilities, because this is at most 2. So the number of terms immediately you get the number of terms in this sum is very small, and then you look at all cases. Okay, and studying all cases, you study this equation, and you immediately come up with the list I just erased of it's like an exercise. This is a standard exercise that you probably saw before. Okay, so Jordan's proof is very much the generalization of this argument. Okay, so Jordan's proof is essentially by induction on n. Okay. Okay, so you induct on the dimension, and you start by noticing that if you have an element g in G, then its centralizer, so the centralizer, and suppose G is not central, then the centralizer of G, you see, so if you can think of, so if G is a matrix, so here at G you are in a finite subgroup of GLNC, so G is semi-simple, so you can diagonalize G. So in some basis, G will be will have eigenvalues like this, and therefore you see the commutator subgroup, so the elements that commute with G will be contained into a block of subgroups like this, right? And let's say U. So if you have n1, n2, un1, un2, and so on. Okay. So then you can use induction on the dimension, and you can. So this is what Jordan does. So every time you have a non-central element, look at the centralizer, and apply the theorem again. Okay. So and use the theorem that you know. So here so if you know the theorem for un1, then you know it for the product of the two. Okay, it's clear. So so in fact Jordan proves something slightly better than that. His proof shows that if you take any field here and you assume that every element of G is semi-simple. So this means it can be diagonalized like this in some basis over the algebraic closure of K. Then G has a So in fact, for the purpose of his argument, Jordan introduces a notion of faisceau. So in French, he calls it faisceau. So I guess in English I should not translate by sheaf because it's already used in algebraic geometry. So let me call it a beam. So what is a beam? It's a diagonalizable subgroup of G, such that when you write it down in such a form, then if you take two eigenvalues, let's say lambda I and lambda j, of an element from that beam, then the ratio achieves many values, or they are the same, always. Okay, yeah. So yeah. So let m be a big number. Then you can define a subgroup F in G is called an n-beam if F is diagonalizable and if for every I and j, the set of values that this can achieve is either 1 or, the size of that is either 1 or larger than m. Okay, so you have, so it's a diagonal subgroup such that so it's a subgroup which looks like a continuous group, if you want. Okay, so you can group together the eigenvalues that are the same, and if two eigenvalues are not the same, then they are not the same for many elements in F. Okay. So in fact, it's funny because when you read Jordan's paper, he does not give an explicit bound on this F of n. So, the later papers by Biberbach and Frobenius, using their geometric method, give an explicit bound, which is worse than this +1 factorial, of course. But Jordan does not give an explicit bound, and although his proof is effective, so he uses the word. He says at the beginning of his memoir, he says that he's going to use two kinds of numbers. Les nombres limités et les nombres illimités. So, okay, yeah. So so exactly. So this reminds me of 19th century non-standard analysis, right? So and that's how he writes things. So. So every time he has a quantity, he knows if it's limited or if it's illimited, which means as large as I want. Okay. So typically here, m will be as large as he wants, and at the end he's going to show that the index of this normal subgroup is a limited number. Okay. Yeah, and but if you want to effectivize the argument, you just have to take at the beginning of a very large n, and see that if you take m large enough at the beginning, you don't have any trouble when you run the argument. Lambda I. So these are the eigenvalues. Okay, so you have the diagonalizable subgroup.
Not the same indexing, so they're indexing more specifically.
Yeah, you're right. Let's call this lambda 1, lambda n. Okay, so you take the eigenvalues, and you say that you look at lambda I mod lambda j. Okay. So if you, in other words, if you have two eigenvalues in F, which can be different from for some element of f, then they will be different for many, many elements of f. Okay.
And what are we proving by induction now?
Okay, we're proving Jordan's theorem by induction. Okay, I haven't even started. Okay, so yeah. So what are we really proving? We're proving that if G is a finite subgroup of G and K, then G, then there exists. Okay, there exists. In fact, there exists f of m, and there exists also m of m, such that G has a unique maximal m beam f, and that Gf is less than f of n. Okay, so this is what Jordan establishes. Here, K is an arbitrary field, and yeah. So of course, an M beam is an abelian subgroup, so it implies the original statement. So okay, so then what will be the analog of the class equation I was writing for the finite subgroups of SO3? Well, what you're going to do is this. So you look at the group G. Inside G, you have the center of G. So, okay, so first of all, you can assume that G acts primitively on Sn. Okay, so otherwise, it means it stabilizes a direct sum of subspaces, and therefore a subgroup of small index will actually fix those subspaces, and you will be inside such a thing, and you just imply induction. Then, but if you act primitively, then a central element will be scalar. Will be a scalar matrix. So inside G, you have the center, which are scalar matrices, and then you have non-scalar, so non-central elements. And if G is non-central, then you can look at its centralizer, which by this argument would be contained into a product of smaller blocks, and therefore you can apply the induction hypothesis. Okay. To this guy, and conclude that it has a maximal M beam inside. Okay, so you have inside an f of G, maximal M beam. Okay, where M is the M for the smaller dimensional given by the induction. And you know that the index here is also a limited number, right? It's a bounded thing. Okay. So yeah. So then, how do you proceed from there? You do as we did for subgroups of SO3. You write G as the union of the center, together with. So you're going to associate. You're going to group the elements together if they have the same if they have the same M beam. Okay, so you group two elements together if Fg is equal to Fg prime. Okay, so let's say that G is associated to F if F equals Fg for some M beam F. Okay, and so you're going to group them. So the union over the M beams of F of the set of G's that are associated to F Okay, so that's what you do. And then again, you're only going to look. So the M beam is like the analog of an axis, if you want. Okay. So then you're going to look at the conjugacy classes. Okay, so you're going to again to group them according to conjugacy classes, G conjugacy classes. So you're going only to look at the union over the classes of M beams, and yeah, and so writing this, so that's a disjoint union, you see, and yeah, so it's not, yeah, so the M beams, then you have to there's this, you have to distinguish a few cases. Yeah, maybe I'll use this board. Yeah, you have to distinguish cases according to what kind of beams you are looking at. So the M beam could be, it could be the center, it could be the scalar matrices, or it could be a non-maximal beam. So every M beam is contained in a maximal M beam because that's by induction. If you take an M beam, look at its centralizer. Again, you can apply induction to the centralizer and get it's contained in the maximal M beam. So every M beam is contained in the maximal M beam. So you have to distinguish between whether F is the center, a non-maximal M beam, or a maximal M beam. And each case, you are going to split this to write G as the center union those elements that are associated to an M beam which is equal to the center, those elements that are associated to an M beam which is non-maximal, those elements that are associated to an M beam which is maximal. And doing this, you get the desired, so Jordan calls it the fundamental equation. Which takes the following form. So here you have the center plus, so you're going to get, so you're going to get things like this. For each contribution, so every number that I write here is an integer, and they're all limited integers. Okay. So by limited I mean that they are given by induction from the theorem in dimension one less. So and so this is the center. This is the part that corresponds to the elements that are associated to a central beam. This is the part that corresponds to the element that are associated to a non-maximal beam and to a maximal beam. Okay, so you get this big equation, and so it takes exactly the same form as for SO3. So you can, if you divide by, so if you let let's say, let's call it G is not a good idea. Let's call it M with G mod Z. Then you get 1 over M is equal to a sum 1 over, so a sum of 1 over, yeah, maybe I'll call this differently. 1 over n i's minus b over a, where the n i's and the b and a are positive numbers. Okay, and integers. Okay. So this is what you get, and you get, but you get that these integers are limited numbers. So they are, they have a bound which depends only on, given by induction, by the theorem, the induction hypothesis. So they depend only on the m you started with at the beginning, and on the dimension. So, but then you have this cute lemma, which I guess I will write here, which is a high school exercise. So lemma. So suppose that 1 over m is equal to this, where everything is where the ni's b and a belong to n. Then either b equals 0, so I think I'm using the French notation for the natural numbers. I'm not sure in England this does not contain 0, but okay, let me take this for them. So either b equals 0, in which case in fact m is equal to n1, and in this sum you have only one term, or b is positive and little m, so suppose you have k terms here, little m is bounded by some explicit function of k and a. Yeah, so something completely explicit that you can write down explicitly, I guess. If you take k factorial a 2 to the k, you're good. Okay. So how do you apply this lemma to our problem? So m here is the ratio between the center and the group and the center. So so if b were 0, yeah, right. And ni is less or equal to m. Okay, sorry, thank you for every I. Okay. Okay, so how do we apply this to our problem? So we have this this thing here. So in the first case, we get that in fact there is only one term, and if there is only one term here, it means that all this term is nothing, and you have only one beam, and everybody is associated to that beam, which precisely means that there is a unique maximal beam. So in this case, you are done, and in the other case, it means that the group is bounded modulo the center. It means that m is a limited number. Okay, because k here is limited and a is limited, so you get a universal bound on G modulo. Okay, so this is Jordan's proof. Yeah. Okay. So maybe. So maybe let me just make one comment. So I think it's quite surprising that Jordan managed to prove that theorem in 1878, because group theory was just in its infancy. And actually, he was not using the words group, but he was using substitution. Okay, so maybe I'll finish by giving a rough sketch of the geometric proof and explain how we can get this approximate version out of that geometric proof. So unfortunately, it was actually one of my secret goals when I started to look at Jordan's proof, was that I was hoping that maybe we could approximate it, but I didn't manage to do that. So. Okay, so let me explain how one can prove how the geometric argument goes. So the geometric argument really requires that you start with a subgroup of the unitary matrices, and it's based on the fact on an idea which I think is due to Bieber-Bach, that if you are near the identity in this Lie group, then if you take two elements close to the identity, the commutator is much closer to the identity. Okay? So you have the commutator shrinking property. So namely, if you have A and B inside UN of C, and A and B are close to the identity, then the commutator, so A, B, A inverse, B inverse, it's much closer in that sense. So there's a constant C such that the distance of the commutator to the identity is less than the product of the distances. So it's a smaller order term. And you see, it's quite clear from that property that that you get almost immediately the following intermediate lemma. That if G is finite, is a finite subgroup of UNC, then there exists gamma in G such that the centralizer of gamma is large. So you get an element with a large centralizer by some function of n. Okay. So so this is the way the geometric argument goes. You have this finite group inside UN of C. You're going to identify an element with a large centralizer. Okay. And once you have found this element with a large centralizer, then you want this element to be non-central. Okay. Non-central. And then if it's a non-scalar, okay. If it's a non-scalar element, then the centralizer, let me be consistent, sorry. Then the centralizer of that element is again a product of blocks, so it's smaller dimensional, and you can again apply induction. Okay. So basically, once you're here, you're done in the proof of Jordan's theorem. And so the key point is to find this element with a large centralizer, and that's easy to do once you have this commutator shrinking property, because you're going to take the smaller, the element closest to the identity. Okay, so if it so happens that this element is not a scalar, then you see that if you take its commutator with any other element, because that's the smallest one, you're going to get something smaller. Okay, so it will be the identity. Okay, so you can do this only in a sufficiently small neighborhood of the identity. But that depends only on something that depends only on n, the size of that neighborhood. So this is why you get here an index that depends only on n. So the geometric argument is much cleaner than Jordan's original proof, I guess. Okay, so maybe to conclude, let me just say that in order to prove that theorem, you can what you do is you first prove that lemma, the approximate analog of that lemma. So you show that in your approximate group A, there is an element an element gamma which commutes with a large part of A, and then you apply induction. Okay. So I'll stop. Okay. Thank you.
Right, thank you very much. Are there any questions?
Emmanuel, so you said at the beginning that post-Jordan's thing doesn't work over arbitrary fields. So where in Jordan's proof is it used that you over C?
Yeah, so as I said, in Jordan's proof, you do not use anything on the field except, you don't use anything on the field if you add this hypothesis that every element is semi-simple. Okay. It's easy to see that this is equivalent to saying that there are no unipotent elements. So if you have a finite group with no unipotent elements, then Jordan's proof works and does not use anything about the field. What's happening in characteristic P is that if you're in characteristic P, an element of order P would be the same thing as a unipotent. And so as soon as you have an element of order P, then you have a unipotent element, and you cannot apply that idea.
Is Jordan's argument also related to the arguments of Larson and Pink? I mean, they have a similar
Right.
sort of.
So I think they have. My understanding is that they first show this non-concentration on varieties, and this then gives very quickly a proof of Jordan's theorem. But in order to, but then later on they use some other ideas similar to the proof of Jordan's theorem. So they also use like a lemma like this, of the type, arithmetic lemma of that type. But yeah, they don't. It's not exactly the same thing. So by now there are many proofs of that theorem.
Okay. If there are no other questions, then I'll just say that Joseph Shomachi is going to speak at 3:15 here again, I think, on geometric instances. And let's thank Emmanuel again.